All right, hey, what's going on YouTube? I think that we're back online, and I'm excited. This is day 9, 10, whatever. Day 9, relearning number theory as a hobbyist right now. And this is going to be fun. So this was the first of all of my videos that I made, and it'll be fun to revisit this topic. I want to talk about number theory, quote unquote, for kids. Really, I mean number theory for everyone. I mean like most people never see number theory, and there is a reason that it is called the queen of mathematics. It's the most beautiful, the most pure, the most fun and delightful kind of math that really motivates a lot of people. So I'm finding that it is a terrific way to generate a lot of little addition problems for second graders that I'm teaching. They find it fun, delightful, interesting. Yesterday, a high school student I tutored was like, whoa, they never teach us this kind of math. They only show us like calculational things. And like that was just briefly showing like one of the problem statements of something I'll be showing today. So I think that there's something there. Like if you present number theory without proofs, like to the right audience, and you hand wave away all the details, these are fascinating facts that are captivating. And I know that I didn't see this math until I was a math major in college. And I wish that somebody had shown me this stuff when I was young. I think that I would have gotten turned on to math way, way earlier. I probably would have gone to math club. I would have done summer camps. I would have done all of those things that would have set me up for a research career. Anyways, 3 topics: Fibonacci, Lucas numbers. And I'm not trying to do this to evangelize people to become research mathematicians. That's not the point. But the point, like part of the point, is just to make math more interesting and fun for everybody. And there's part of my brain that's just always thinking about what is AI going to do to the world. And one of the things, because AI is going to change everything. I worked in Silicon Valley. I'm one of those people who really knows like how much AI is going to change everything, or believes that, I suppose. I think it's going to change a lot. I think one of the things is that there's going to be more increase for advanced and difficult mathematics. Stand strong. There was a question of Fibonacci and promise application problem set. That's so funny that you mentioned that, because somebody was just telling me about promise and how cool this program looks. I've never seen it. Stand strong. Did you apply to promise? As I understand it, it is a summer camp in math. I know somebody who went to that and highly recommends it. So yeah. I am running late today. For better or worse, I think it would be good to get a 30-minute video on this channel instead of always 2-hour practice sessions for myself. So let's just jump into it. I want to just jump right into this stuff. Let's jump into Fibonacci, and this time we are going to also introduce the Lucas numbers. So I didn't know about this whenever I did my first video on number theory for kids. But then I introduced the Lucas numbers in a future video that was more geared toward myself or other people doing rigorous, pure mathematics. But I think that this is super cool, because like there's one kid that I'm working with who's really good, and he finds it so much fun to do addition problems, but he like still does finger counting. Like I can hear him kind of like sub-vocalizing like 11, 12, 13, 14, 15, 16, but he's so passionate and loves adding, but he's still kind of counting, but he's counting so quickly and with such enthusiasm that I don't want to like correct him and say, no, that's the wrong way to add numbers. So I'm trying to find ways to like make it to where like, yeah, that's a great way. Like you're having fun with that. Keep doing that. But now these numbers are going to get bigger. You're going to have to do, harder problems. So he really likes the Fibonacci numbers. Let's revisit it for everybody. You start with two numbers, okay? Simplest thing. Stand strong. Yep, you applied, but selection in our country is less than 1%. Dang. Okay, well, good luck next time. I bet that if you keep showing up to this stream, we're gonna get you in shape and we're gonna get you into promise. That's so cool. I just heard about this program recently. I don't think it existed when I was young. Anyway, so you just write down two numbers. Let's not make this formal. Don't use scary symbols if you're teaching kids or a retiree, like adults who haven't seen math in 40 years or whatever. Yeah, you know what I mean. So write down two numbers and then you say, add the last two numbers. What is 1 plus 1? 2. What is 1 plus 2? 3. What is 2 plus 3? Like, you just say that. You don't even have to say add the last two numbers. Just keep saying, what about 3 plus 5? 8. And then 5 plus 8. And then maybe this kid that I'm working with would go, 9, 10, 11, 12, 13. You know, like really quickly say it. But he's enjoying it a lot. So it's like, okay, cool. Now 8 plus 13, 21, you know. So this has been a great problem, and I'm like, I'll be like, okay, now you work on that for a little bit, and then I'm gonna check in again, and then he gets so far, I'm like, oh, you got to level, I don't have them memorized, you know, but you got to level 20, but then you made a mistake here. We'll see if next time you can get to level 30. Like, I try to use, like, some video game terms and whatnot, and he finds it fun. But now, the problem is that I think I'm starting to see that he's starting to have them memorized, which is a good thing, I think. It's not the worst thing in the world to memorize the Fibonacci sequence. I think that's way better than memorizing the digits of pi. Who cares if you know the digits of pi? Like, who cares? Doesn't matter. But Fibonacci numbers, that's a way better sequence to memorize, I think. So he's able to start writing down the first few pretty quickly and then has to actually start practicing math. So I think that's a good thing. So I can just let him get to that far before he starts to actually start doing math and writing things down. Also, again, this is a great place if I am watching him or anybody do this problem and I see that they start doing 89 and 55 like this, I'm like, that's really great. That's a good way. That's the best way if you want to, if you have your pencil and paper. If you have pencil and paper with you, that's the best way. Write it down. Do it like this. That's going to work for 4 digits, 5 digits. It doesn't matter how big the numbers are. You can always do that. That's pretty good. But if you're at the grocery store and you want to add these numbers, like, what about 55 plus 100? What is that? 155. Okay, now what is 155 minus 11? 144. Like, those two math problems are way faster to do than the one original math problem. And I hope we can all see why. I shouldn't say I hope we can all see. I would say to the kid, like, do you see why that's the same? Do you see why that got to the same number? Well, it's because 89 is 100 minus 11, right? So if you add 100 and then subtract 11, then that's the same thing as adding 89. And that's easier. That's like anyway, so here is a great problem for everybody who feels rusty about addition, or maybe you're learning addition for the first time and you're in school. It's a great place to practice and drill addition. It's a great place to drill mental arithmetic and mental math, mental calculation. Okay, so that can work. You can get somebody to just start writing down the Fibonacci sequence as long as they feel like it. Tell them to do it before falling. If you can't sleep, try just running through Fibonacci numbers in your head. Instead of counting sheep, try to just list Fibonacci numbers. I don't know if that's a healthy thing to do or not, but I'm not a doctor. Okay, well, now we're going to introduce, like, recently I was like, okay, guess what? Did you know that the Fibonacci numbers have an evil twin? They have an evil twin. The evil twin of Fibonacci is Lucas. Lucas is the evil twin of Fibonacci. It's the exact same thing, but this time we start with 1 and 3. Okay, but we're going to do the exact same thing. What is 1 plus 3? 4. What is 3 plus 4? 7. What is 7 plus 4? 11. 11 plus 7 is 18. 18 plus 11 is 29. 29 plus 18 is 47. 47 plus 39 is 76. Right? Etc. So this is another sequence of numbers, and yeah, it's just another sequence that maybe eventually he'll memorize this sequence too, but then at that point maybe his addition has gotten pretty good. But this is great because then now it's just another sequence of numbers that you can memorize, and honest to God, I knew, like, I have seen the Fibonacci numbers before, and if somebody said 55 or 55 or 89, there's a chance that I might have been like, oh, that's a Fibonacci number, I think. Like, let me run through it. Yeah, that is a Fibonacci number. Like, I have some familiarity with these. 34, 55, 89. Like, I know that those are Fibonacci numbers. I honestly did not know about the Lucas numbers until I just recently started working through this book. And I've taken a number theory class. Maybe it was an exercise and I completely forgot it, and I was just treating it as a way to learn a more important mathematical technique of mathematical induction. And math induction is the point. Who cares about Lucas numbers? It doesn't matter. The only thing that matters right now is learning proofs. No, like, this is fun. This is cool. So here's a delightful other sequence. Well, why is that interesting? Well, for one, it's just the same pattern. Add the last two numbers. But now, what about 1 plus 2? 1 plus 2 is 3. What about 1 plus 3? 1 plus 3 is 4. What about 2 plus 5 is 7? And then, like, when I've done this, the kid immediately saw the pattern after just, like, a couple examples, and it was like, 3 and 8 is 11, 5 and 13 is 18, 8 plus 21 is 29. And it's like, what? I just discovered something really cool. You know? Like, he's like, whoa, if you add those two, then you get that one. It's like, yeah, that's freaking cool, right? Like, isn't that freaking cool? If you add two Fibonacci numbers that are apart, you get the Lucas number in between. That's neat, you know? So I wouldn't show this notation to a kid, but the Lucas number n is Fibonacci, the prior Fibonacci number plus the next Fibonacci number. And you can prove that using mathematical induction, or probably just from the properties of the Lucas numbers. You can take one of them as a definition and then prove the other, that you get the recurrence relation, and the prior and then the penultimate Lucas number, like the last two Lucas numbers add together to get the next one. I think that you can take either of them as a definition and then prove the other. So I just think that's delightful. I think that's so cool. But then you can take this even one step further. And I can say, you know what? Let's pause for 1 second. Because I have something even cooler. Before you show a kid the Lucas numbers, which is like an entire other world that you're introducing them to, an entire other world of another sequence. Before you show them the Lucas numbers, first show somebody this. Like, let's get rid of all the Lucas numbers. I hope my iPad's still working. It is, good. Okay, so let's get rid of all those Lucas numbers. Now, I want to ask, okay, what happens if we add, what is it? I forget. Yeah, okay. All right. 1 is 1. What about 1 plus 2? Let's create a table. What is 1 plus 2? 3. What is 1 plus 2 plus 5? 3 and 5 is 8. So, yeah, 1 plus 2 plus 5 is 8. 1 plus 2 plus, and I tell anybody, like, oh, you'll see where we're going with this soon. Right now it might seem weird and random, but 1 plus 2 plus 5 plus 13. And like the little kid that I was working with would redo the whole problem. 1 plus 2 is 3, 3 plus 5 is 8, and then 8 plus 13 is 21, right? But then that's a good opportunity to show somebody like essentially a computer science technique of computing. It's like, oh, but notice that we already calculated this part here. So all we care about is the last answer and then this extra number, right? So what is 8 plus 13? 21. Okay, so I'm going to use ... to mean all of this previous stuff that we've added together. What is that stuff plus 34? Okay, so we add 21 and 34. Now that I'm doing it this way, now that I'm showing it on an iPad and I'm like self-criticizing while I do it, maybe it's clearer if I show that once and then say, okay, so this is ... but what it's going to add up to is 21. So what is 21 plus 34? So I'll just write it there. 21 plus 34 is 55. I think at this point, we're some little bells are going off like, wait a minute, 55? That's one of those numbers that I often recognize as a Fibonacci number. Okay, wait a minute, I have an idea. Let me take a look. 55 is there. 21 is there. 8 is there. 3 is there. And then 1 was the first one, and it's right there. What? If you add some Fibonacci numbers, then you can get another Fibonacci number. So how do we formalize this? How can we make this a little bit more rigorous? So on the right-hand side, we circled the ones that were the answer, right? Maybe I'll draw that in a red pen right here. Maybe on the left-hand side, I'm going to circle the numbers that we were adding. The first time it was 1, then we added 1 plus 2, then 1 plus 2 plus 5, then 1 plus 2 plus 5 plus 13, right? Oh my gosh, isn't that so cool? We're circling every Fibonacci number. 1 plus 2 gives you 3. 1 plus 2 plus 5 gives you 8. On and on forever. Like, isn't that a super cool, delightful identity? To know that you can like add together Fibonacci numbers to get another Fibonacci number. Maybe it seems obvious and like you can figure out why as a good exercise, but it's a really cool thing to show people, I think. I think if we write it out this way, the notation is f2n minus 1, f2n. So if we add n odd terms, then we get Fibonacci 2n, I think. Cool. All right, you still with me? Like, I honestly think that that's a very cool fact. So that's where I was pulling 1 plus 2 plus 5, 1 plus 2 plus 5 plus 13, 34. Then the next one is going to be 89. Oh, wait, no. Plus 34. Oh, the blue ones. Yeah, the blue ones are, yeah, okay, 34. So then the next one is 55 plus 89. And we saw before that that's 144. 55 plus 89. Cool. Well, 55 was the sum of the prior one. We might start to see a mathematical induction happening here. Cool. So that's a really fun fact. Now, then on another day that you're working with somebody, then maybe you show them the Lucas numbers and you show them that first math fact that's super freaking cool, about how the apart, like Fibonacci numbers that are apart equal the Lucas number in between if you write them out in a list like this. I think that's super delightful, just on its own. But now, another day, what I love here is that this can now turn into a way to practice multiplication. Okay? So I'm going to give some multiplication problems. Well, what is 1 times 1? That's easy. That's 1. What is 1 times 3? Maybe I'll give us some more space here. Why don't we give just a lot of space? All right. What is 1 times 3? Well, that's still easy. Why are you asking me that? What about 2 times 4? Maybe you ask these verbally and you're not writing them down yet. 2 times 4 is 8. What about 3 times 7? 21. What about 5 times 11? 55. What? Wait a minute. The right-hand side is starting to sound very familiar. What about 8 times 18? Okay, here's a great mental math problem. I'm, in my head, doing 8 times 20, which is 160, and then subtracting 16 from that. So that's 144. So depending on the person that you're working with, whether they need more practice with the algorithm, table, column way, or mental math, it's a great, or for yourself, like, do either of those approaches. Okay, and now we're going to start getting some bigger and bigger Fibonacci numbers. 13 times 29, I think, I don't know, that's 290 plus 60 minus 3. 290, 350, 347? Is that right? Did I just do that? I'm getting better at mental math, y'all. From teaching kids, I think I am literally getting better at mental math. 9 times 3, 27. That's easy. So 6, there's an 8, 9, 2. So 7, 17, 3, 7. Okay, well, I was a little bit off. I screwed that up. Oh, well, whatever. 377. You can tell that I don't know my Fibonacci numbers that far. And Stan Strong says 377 then. Yeah, I got it off. But got it wrong. Oh, well. So as you pointed out, though, 377 is a Fibonacci number. So something is happening here. And as you pointed out, the next one here, following the prior pattern, is 377. There's no way that's a coincidence. It's the same numbers again. It's the same sequence again. Well, but how was I getting the left-hand side here? What am I multiplying? How am I doing these multiplications? If you haven't seen it yet, it's right here. Lucas numbers. multiplied with their twin Fibonacci numbers. So 1 times 1, 1 times 3, 2 times 4, 3 times 7, 5 times 11, 8 times 18. I did all of these so far. Okay? So at least I can draw up till this last one. 8 times 18 is 144. 5 times 11 is 89, right? Oh, wait, no. 5 times 11 is 55. 3 times 7 is 21. 2 times 4 is 8. 1 times 3... Okay, I should have used a different color for these arrows, but that's okay. Maybe... we're running out of colors. Purple. Okay, so 1 times 3... Yeah, so again, I mean, maybe you can just see it from the original arrows or whatever, but we're again getting every other Fibonacci number again. Isn't that dope? Damn, I know, right? Isn't that a fun one? And that's just like, what? It's not only a interesting relation, but it's the exact same relation. Like, it's the exact same right-hand side. I mean, like, what? That's cool. And I have shown the technique of math induction. Y'all can try to... Why did you retract your message? Keep it. It's great. I mean, damn. Like, that is like a... Damn, that is cool. Like, what? Cool. Like, I want to understand why. Maybe it'll be obvious. Maybe it's like a magic trick that seems amazing, and then you think about it, and then it's like, oh, okay, no, now that makes sense. Yes and no. Like, it's no longer... The magic is gone for me because of math induction. I know that this is always true, but there's still some magic in it to me about a geometric or like a reason why. Like in terms of like a reason, like what does the Fibonacci numbers mean in terms of counting objects and how they're like compound growing. And I bet that geometric or that sort of like intuitive understanding exists, but I don't want to ruin the magic for myself. I'm going to leave that magical because I still find some magic and delight in that one. So that's a fun one. I'm running out of time. No, it's not offensive. No, this is a PG-13 channel. Yeah, just don't get like super rated R too often. But yeah, you have a great problem. Go ahead and say it, but I'm running out of time, so I'm not going to work it. But feel free to please drop it in the chat. So next one. I briefly stated this in the first video, and I want to make sure I give this a little bit more time, a little bit more careful energy. Collatz conjecture is incredible. It's just such a perfect problem, I think, to show kids, like to show a fifth grader or anybody really, because you only need simple math, right? And I draw it this way. You've got two machines. And some people have seen functions, some people haven't seen functions. Some people have seen these machine diagrams and others haven't. And I'm going to say, okay, I have two machines, A and B. One of them will divide by 2, and B, the other one will triple something and then add 1. Like, I say verbally triple and add 1. And, like, not everybody has even seen X yet as a variable name, but it's just like, don't worry, that means triple a thing and then add 1 to it. And they're like, okay, I know what triple plus 1 means. All right. And then I say, okay, the way I'm going to write this is, well, first... If I give the number, let's say 2 to the machine A, then what does it return? Well, what is 2 divided by 2? That's 1. Like, I could write it like that, or I could say 2 goes into A, and then A returns 1. What is like, it doesn't matter. Here's some just different ways to draw the same thing. But a is always going to divide by 2. So 4 divided by 2 is 2. 8 divided by 2 is 4. Okay. One way we can write that is like this. If I give the number 8 to the machine A, then it returns 4. If I give the number 16 to the machine A, then it's going to return 8, etc. Okay, what about machine B? If I give the number 1 to B, what do you think it returns? So again, B triples and adds 1. So that's going to give you 3 times 1 plus 1 is 4. If I give the number 2 to B, so what is triple 2 plus 1? It's 7. So triple 2 is 6, and then add 1. So this is a fantastic way to practice your 3 times table and to teach a 3 times table to somebody. All right, so what is 3 times 3 is 9. Okay, let's just add 1 extra to that. All right, what is 3 times 4? 3 times 4 is 12. Add 1 to that. Okay, so we're getting the hang of this. Now, I'm going to define a much more fancy machine, C. This one is going to be a little bit more complex. It is going to use A if the number is even, and it's going to use B if the number is odd. Okay? So, what is C of 1? Well, 1 is odd, so it's going to use the machine B. What does B do again? Triple plus 1. 4. What does the machine give for C of 2? Well, 2 is even, so we use machine A, and then what is half of 2 is 1. All right, let's give one more example. C of 9, maybe. 9 is odd, so we use the second machine, and we triple plus 1 odd numbers. That's going to be 28. Okay, so those are some good examples. Now, I'm going to show you something incredible. We can start with any number, and now I'm going to start listing numbers in a row. Each time we're going to keep giving the number to machine C. So, what is triple plus 1? 5 tripled plus 1 is 16. Okay, what is half of 16? 8. What is half of 8? 4. What is half of 4? 2. What is half of 2? That's 1. Okay. All right. What about if we start with 6? Half of 6 is 3. Triple plus 1 is 10. What is half of 10? You know what? I don't usually do this one, but it works nicely. Okay. Half of 10 is 5. All right, and now we've already done 5, right? Right before this, we just did 5. So we can write down the exact same numbers. 16, 8, 4, 2, 1. Or I could just say ... We've already done this one. We know that it eventually is going to go down to 1. Okay. That's where you start introducing the idea, like, eventually this thing gets to 1. All right, one more, 7. Triple plus 1. What is 3 times 7? 21. Add 1 to that, 22. 11. Triple plus 1, 34. Half of that, 17. Triple 17. This one's a little bit tougher for kids. But you can see, I think of that as 10 tripled and 7 tripled. That gives you 51. So the next number is 52. Half of that is 26. Half of that is 13. Triple plus 1. I'm running out of time, so I'm going to go quicker. 20, 10, 5, And now, ... we've already done 5. So we know all of those numbers, and it ends up finishing at 1. So even though 7 was just a little bit more than the prior ones, it ended up being way bigger. It ended up taking a lot longer. There were a lot more calculations we had to do. But other ones are quick, like 8, 8, 4, 2, 1. So, depending on the person, if you just want to practice tripling and dividing by 2 in your head, this is a great way to count sheep, metaphorically. Like if you're in the grocery store and you're just like, I'm stuck, I have to think about something, I don't want to think about social media. What happens if I start with 15? 46, 20, 23, 60, 70, 35, and then like sometimes they get bigger, sometimes they get smaller. Like it's a fun way to practice mental arithmetic of tripling. And then if the person is ready for it, you can really, I like to show this to anybody. What I say is, what is incredible is that we think that no matter what number you start with, n can be any number, no matter what number you start with, this always works. It always ends up going to 1. Sometimes it takes a very long time. Sometimes it takes super, super long, but eventually, if you keep giving numbers back again and again to see, then the chain will end at 1. And that's incredible because we don't know why. I write this in like capital letters or something for a kid. We don't know why. And then I draw a smiley face because it's like, that's fun. People have found this fascinating and beautiful and some people have dedicated many years, if not their entire career, probably somebody out there, to this problem. And we consider it very hard still, and it's still an unsolved problem. So if you can figure out why, you would be very famous. I think it's a really fun thing to show to a kid and to anybody, because I think, like, I'm working with like high school kids who still have never seen the idea that there are unsolved problems in math. And that's incredible, right? Like, it's cool to show an actual unsolved problem to a kid that you can explain that feels just like their worksheets, but it's so much more fun and interesting, and there's way more motivation. There's like a reason that they're multiplying and learning their 3 times table. So, I don't know. What do you think? Did you enjoy this? Try it. Like, literally, what do you think? Pedagogically, I think it's unknown to me. Like, is this a good idea or not to teach unsolved math, like open problems in math, as a motivating problem for simple arithmetic to kids? I mean, like, Lucas numbers is not unsolved, but I think that that's another fantastic motivation. So that's it. Thank you everybody for watching. I had a lot of fun this week practicing number theory. We are going to switch gears. Next week I'm on vacation, so absolutely no social media, no YouTube, no computers, just pen and paper and oil lamps, and I'm going to be on vacation. But I will be practicing math as a hobby, for fun, for myself. And we will be back the following week. In 2 weeks, we are going to be revisiting our favorite ChatGPT math, linear algebra, so I can get a job again someday. All right. Thank you all for watching. Like and subscribe. I hope you enjoyed this. I hope you found this fun. I certainly did. All right. Bye. Thanks, everyone. Bye. We didn't. I'll just say one last thing. We did not get to subgroups of a clock. Try to imagine for yourself what that might mean. I tell kids that your favorite TV show's at 1, and you need to keep taking naps or you're doing homework for 2 hours at a time. Will you ever see your favorite TV show? And other things like that. Okay, so cool. Stand strong. I do see your problem. Thank you. I will try to take a look at that on vacation.